So these are the notes for lesson 1.7. What we're going to do is start off by looking at intervals where functions are increasing, decreasing, and are constant. And then we'll recognize relative extrema as well. All right, to start off with, I would like for you to go through on your graphs and label the parts and pieces that you see. For example, this part here, I'm going to put a C and a C here. And the C stands for constant. Those will be the horizontal pieces. And then I'm going to put D here for decreasing. As I read the graph from left to right, it's going downhill. The intervals for increasing, decreasing, and constant are always going to be in terms of the domain or the x values. So for constant, my graph is constant from the left side here of -4 and from 2 out, so 2 to infinity. It is decreasing from my x value here is -4, and over here my x value is 2. Notice that I don't use any brackets on these. I will use the square brackets that look like this only when I talk about domain and range. For intervals of increasing, decreasing, and constant, we are using parentheses. This graph does not increase, so I'm just going to draw a line through it. This graph also does not have any relative minima, or maxima. These are plural for minimum and maximum. I will have a minimum, which basically is a low point in a graph, when my graph goes from decreasing to increasing, and I will have a relative maximum when I go from increasing to decreasing. So when we switch over, we'll have either a minimum or a maximum. So this would be a min, this would be a max. Okay, it's not letting me write up there, so let me clean that up real quick. This is a max. Okay. Let's look at this one. So I'm going to start again by identifying the pieces. As I go from left to right, this is decreasing, increasing, decreasing, increasing. So we're increasing here and here. So the x values are -3 and 0, and a comma instead of the union sign, and then 3 to infinity. So 3 and to the right. We are decreasing. Let me grab a different highlighter. We're decreasing here and here. So that is -infinity to -3, and then 0 to 3. Those are the x values for the blue highlighted pieces. Constant, we are never constant. All right, we do have 2 relative minimums, and they are here and here. So we say we have relative minima at x equals -3 and x equals 3. Okay, another way to say this, we have relative minimum values of 0. So we're talking about the y value when we talk about value of 0 at x equals -3 and 3. And finally, you can say you have relative minima, oops, spelling it wrong, at, and then you can name them as ordered pairs. So there's basically about 3 ways to say the same thing. For our maximum, that's going to be the point up here at the top. We'll have a relative maximum value of 4 at x equals 0, or I can name it as the ordered pair 0, 4. All right. We're going to test for symmetry. This graph up here has what we call y-axis symmetry. So we would call that an even function. We're going to be talking about things like that here coming up, but in terms of equations rather than graphs. All right, there are 3 tests for symmetry that we will follow. First of all, I'm going to sketch in a little picture of a graph that has y-axis symmetry. And that happens when we get the same y value for an x or for its opposite. So the test will be to replace the x value in our equation with a negative x. If I get the same equation back that I started with, then I have y-axis symmetry. For x-axis symmetry, that's going to be a graph that is reflected over the x-axis. We will replace y with negative y. And for origin, x to the third, y equals x to the third is a good example there. You'll do them simultaneously. So the test works like this. You're going to replace x with negative x or y with negative y or both. And if you get the same equation back that you started with, then the equation has that type of symmetry. So we'll apply that here to our first example. All right, basically you're going to be testing 3 types of symmetry for each one. So I'm just going to come through and make a table. We'll do x-axis, y-axis. Let me do that in a different order. That way it stays consistent with the table up above. So we'll do y-axis, x-axis, and origin. All right, part A. So the goal here is for y-axis symmetry to pull out x and in its place put in negative x. Manipulate that, so clean it up. And then I'm going to compare, is this the same equation that I started with? The answer is no. So then I'm going to move over to x-axis and try again. For x-axis, I take out y and put in negative y. Okay, if I square negative y, I'll have positive y squared. I'm still subtracting right here. This equation is exactly what we started with. They match. So we do have x-axis symmetry. For origin, I'll do the 2 tests together. And I'll clean it up. And again, that negative that's in front of the 2x is what's throwing it, so we don't have origin symmetry. So this problem, this equation only has x-axis symmetry. Now let's try y equals 2x to the third. So for y-axis, I'll take out my x, put in negative x, and cube it. Cubing a negative is a negative. These 2 are not the same, so we don't have any symmetry for the y-axis. For x-axis, I'll make y negative y. I can switch my negative to the other side by dividing both sides by -1. And again, we don't have that type of symmetry either because this new equation doesn't match that one either. But let's do them together at the same time. So we'll have negative y equals 2 times negative x to the third. Negative y equals negative 2x to the third. I can divide both sides by a -1, And I end up with this right here, which is exactly what we started with. So this function, or this equation, has origin symmetry. All right, the next bit is even versus odd. In a nutshell, functions here, let me just write it in the table. Functions that have y-axis symmetry are even, and if they have origin symmetry, they're considered odd. So you'll remember that because origin and O start with O, or origin and odd both start with O, and then even is just going to be folding it over the y-axis. In terms of functions, we know that functions are written with f of x instead. So the rule or the test becomes, we're going to say, is f of negative x the same as f of x? In other words, when I put in negative x, do I get the same y value back as putting in x? And then for origin, you'll be looking for the opposite of the function. So let me model that for you here. All right, what happens when I do f of negative x? That simply means I'm taking out x and putting in negative x. And then I'm going to clean that up and see if I get the original function back that I started with. All right, it is not exactly the same, but I notice that my signs here and here are opposite, here and here are opposite. So what I have here is the opposite of the original function, which is then negative f of x. Hence, this function has origin symmetry, or it's considered odd. Let's try another one. I'll plug in negative x. And I'll have x squared minus 2x. Okay, this one doesn't show up as exactly the same or opposite. This sign is different, but the sign in front's the same. So this one is neither even nor odd. So this one does not have any y-axis or origin symmetry. Okay, the next topic in this lesson is a review of piecewise functions. So I'm going to open that up with a word problem just to show you where in real life you're going to see these and how to interpret them, and then we'll go through the problems that I have. All right, a telephone company offers the following plan. You're going to pay $20 a month for 60 minutes, and additional time is 40 cents a minute. So let's set that up with a piecewise function. We're going to pay $20 when x, which is our time, is less than or equal to 60. So for 60 minutes or less, you pay $20. And then for time over that, we're still going to pay our $20 up front. And then we're going to do 40 cents. And then x minus 60. So this is for any time over 60. So if you talk for 70 minutes, you're going to put 70 in for x, and then your overage is 10 minutes. 10 times 40 cents will be added on to your $20. If I'm finding C of 30, this represents talking on the phone for 30 minutes. 30 minutes is less than 60, so my bill will be $20. So this one goes back to the first function. If I talk for 100 minutes, that is greater than 60. Let me use a different color here. So 100 is greater than 60. So I'll use the second function for the second part. 20 plus 0.40 times 100 minus 60. So 20 plus 40 cents times 40. So there's $16 there that you're going to add to 20. Your bill would be $36. Okay, so there's a word problem with the piecewise function, and then you have just these ordinary problems. This piecewise function has 3 parts. We have a part for when x is less than 3, x equals 3, and x is greater than 3. So the first thing you're going to do is you're going to look at the 5. 5 is an x value, so this is just saying x equals 5. Is 5 in this group, or this group? So 5 is greater than 3, so I will be using this function, 2 times 5 plus 5. So the 5's going in right there, and that's 15. All right, when x is 3, the answer is 5. That's using the second piece. And negative 2 is definitely less than 3, so I'll plug it into the first function. And there's 9. Okay, now we're going to come through and try to write an equation for this piecewise function. So piecewise functions, when graphed, typically produce these discontinuous graphs. Some do connect up, this one does not. So we're going to start with f of x. We're going to put up a bracket. Okay, it looks to me like this branch here is x squared. And why do I know that? How do I know that? 1, 1 is a point, 2, 4 is a point, 0, 0 is a point. So x squared. It is only on the right side, so that's when x is greater than or equal to 0. And this initial point was filled in. So that initial point being filled in indicates an equal to right here. This over here on the left is a line, part of a line. It has a slope of 2/3, and it's a positive slope. It's going uphill. It has a y-intercept here of 1, so my slope is 2/3, and then my y-intercept is 1. So that would be the line y equals 2/3 x plus 1. But it's on the left side of 0, so we're going to say x is less than 0. It also has an open circle on the end, which corresponds to just our less than sign. There's your piecewise function. Now, the last part is, how do I graph them? Okay, so up here we went from the graph back to the function. Now we're going to go from the function to the graph. What I like to do is split it into 2 XY tables. And I'll use 2 different colors. All right, from here, I will be putting in values less than 0, but I do need a starting point, so I am going to go ahead and start it at 0, but because it's not equal to, when I graph it, I will be using an open circle there. For this one over here, I will also start it at 0, but it's underlined, it's equal to, so when I graph it, I will be using a closed filled in dot there. Now, for the first one, it says I'm going x is less than 0, so I'm going to go less than 0 just a few times. Plug those in. And then for the orange one, I'm going to be taking the square root, so I'm going to pick some perfect squares here. The square root of 0, 1, 4, and 9. And then I'm going to graph. So 0, 0, first of all, for my blue function, has an open hole. And then negative 1, 2, negative 2, 4, negative 3, 6. All right. It says x is less than 0, so this continues going to the left. So go beyond the points you have to the left. Over here, 0, 0 is my starting point. It's closed in. So when you have this tug of war, one's open and one's closed, you're going to be filling it in. And then graph your points. And this one continues to the right where x is greater than or equal to 0. All right, so this graph actually ended up being continuous. You can trace it without lifting your pencil. Let's try this one. And this is the last example in our notes. So the video is almost finished. All right, for the first one, we have that. And for our second one, we will have this. All right. All right, again, I'm going to look here to see where I start my table. I'm going to start this one at 2, and it is equal to, so that tells me my opening point will have a closed-end dot. And then I'm going to go less than 2, so things less than 2, like that. And then for the orange one, it's greater than 3. So I will start with 3, but because it's just greater than, I will have an open circle. So that way we can graph all points up to 3, but not including 3 when x is 3. We want to go greater, so let me pick the orange pen back up. We'll go bigger. Okay, so let's plug those in and calculate. 2 squared minus 4 is 0, and then 1 minus 4, 0 squared minus 4, and then back to negative 3. Plugging in 3, 6 minus 4, 8 minus 4, 10 minus 4. And then let's plot our points. So 2, 0 is closed, 1, negative 3, 0, negative 4, 1, negative 3. Now, this is continuing to the left here of 2. So we want to have this as our starting point, and then this is a parabola that just keeps on going. So it does look like a fish hook. We have a starting point on the right, and then it continues going on the left. The other piece is linear, so we'll have a line coming out of the other piece. 3, 2, 4, 4. Oops, let me graph that in the right place. 5, 6. And then we will connect up there. This graph would be discontinuous. Just for fun, if you wanted to state the domain and range from these, this is good practice for you. The domain on this one is actually all reals because it continues from the left to the right. Your range, the lowest point here is at 0 and it goes up. For this one, your domain, it's coming in from the left and it stops here at 2. So negative infinity to 2, union, and then it starts back at 3, but it's an open circle and goes to the right. If you wanted to do the range, your lowest point is down here at negative 4. And then it goes up. It continues going up, so to infinity. Oh, and I was going to erase this to get that stuff out of the way. Okay, so there's your range. Go back and finish up your notes, and then go ahead and try your Alex assignment over this lesson 1-7. Reach out if you have any questions.